Welcome to our third module, which is dedicated to quantum factoring. Today, we're going to recap the number theory background that is necessary to understand Shor's algorithm. In particular, we'll start with congruences. This is going to be a very important element of Shor's algorithm. We say A and B are congruent to a modulo an integer n, which is strictly greater than 0, if n divides b minus a. And we denote that by A congruent to B mod n. So for example, you have that 4 is congruent to 1 mod 3. Okay. You also have things like you can have a negative number. So for example, minus 2 is also congruent to 1 mod 3. This is not to be confused, of course, with the value A mod n, which represents the remainder of the integer division of A by n. Now, this notion of congruence gives rise to the notion of congruence classes. The congruence class of an integer A mod n is all the x's that are congruent to A mod n. So, using the previous example, what you have, if we denote it like this, so sometimes we use brackets, sometimes we use bar. This is a set, of course, and it's going to contain infinitely many elements. In particular, it has minus 2, it has 1, it has 4, it has 7, etc., etc. This is, of course, understood mod 3, okay? Now, we can treat those congruence classes as elements on which we can perform arithmetic operations. A lot of the times, we identify a congruence class with the unique element between 0 and n minus 1 that is inside of that congruence class. Okay, it's sort of a unique representative this way. However, it's usually an abusive notation. What we really mean is we're dealing with an infinite set, and in theory, we should put brackets or bars above the numbers. But sometimes by abusive notation, we tend to cut some corners and identify that with this unique number between 0 and n minus 1. In any case, we can perform arithmetic operations, and particular addition and multiplications are very well defined as follows, which is that we define the sum of two congruence classes by the congruence class of the sum of two of the representatives of the congruence classes that we have here. And likewise, we have the multiplication of congruence classes as the congruence class of the product of a representative of each of the congruence classes that we're trying to multiply. So for example, if we're trying to multiply modulo 7, let's start by adding modulo 7, 4, and 3, this is the class of 7, which is also the class of 0. And the class of 3 that we multiply by the class of 4 is going to be the class of 12, which I can simplify as saying this is a class of 5. Now, one of the very important arithmetic operations that we're going to need inside of Shor's algorithm is exponentiation, okay? And it derives from the fact that, in fact, you have to exponentiate for example, RSA, the RSA crypto system requires you to exponentiate large numbers. And this is also something that happens inside of Shor's algorithm to break the RSA crypto systems. You need to figure out a way to efficiently exponentiate a congruence class modulo a large number. So we assume that what we need to do is this operation here, okay? And like I said before, here we're talking about calculating the remainder of a to the x modulo n, okay? And it will uniquely identify the class of a to the x modulo n, okay? So we decompose first x in binary, okay? This is the binary decomposition. And then we perform the following operations. We calculate the a to the 2 to the I for I between 1 and k, where k is the largest power here occurring in the decomposition of x in binary. And then what we can do is we rewrite a to the x as a to the x0 plus x1, 2 plus x2 to the 2, etc. And we can say, well, this is a to the x0, remember x0 is either 0, 1, times a to the 2, which itself is to the x1 or x1, which is 0, 1, times a 2 to the 2, okay, to the x2, and then multiply ultimately by a to the 2 to the k to the xk, okay? So each of these elements, of course, come from our pre-calculation, and so we're just multiplying together, and then, but we decide whether or not to put them in this product if with respect to the values of the xi. So if an xi is 1, then that value that we pre-calculated here is going to occur in the product. If not, then we just simply skip it in the product. So let's work it out in an example. So a here is 17. So a equals 17. So a equals 17 and x also equals 17, which is 16 plus 1, okay? So here we have that 17 to the 2 is modulo 23 is equal to 13. Now 17 to the 4 mod 23, efficiently I can do it by saying this is also the same as 13 times 13 mod 23, and that is equal to 8. Now 17 to the 8 mod 23 is equal to 8 times 8 mod 23, and that is equal to 18. And finally 17 to the 16, which is the last term that I need to pre-compute to perform this fast exponentiation. This is 18 times 18 mod 23, and that is equal to 2. Now finally 17 to the 17 mod 23. I only have two terms here. I have 17 to the 16 times 17 to the 1 mod 23. And that in turn is 2 times 17 mod 23. And that is equal to 11, okay? So the takeaway here is that even when we have a large number in our exponentiation, we can perform this exponentiation in a number of operations, number of elementary arithmetic operations that is going to be small with respect to that number. It's going to be essentially of the length of its binary. The number of operations is going to be proportional to the length of the binary expansion of the exponent, right? And so what it means is it's going to be very efficient as the exponent grows because it's log of the exponent rather than a naive way, which would be multiplying 17 as many times as required, okay? Now, of course, what it means is we also have a fast exponentiation circuit, okay? So with the methods that we described before in the previous lectures, we'll be able to derive an efficient quantum circuit that produces reversibly this operation, okay? And this is something that we'll be assuming inside of Shor's algorithm, okay? So we will need something like this, and we know that it is possible through generic methods that we mentioned in the previous lectures. Now, another very important operation, a very important aspect of Shor's algorithm is Chinese remainder theorem. So it's something that we need to mention here. Assume A and B are co-prime, then we have this isomorphism here between Z mod NZ and Z mod A and Z mod B. So here, this notation, let's be specific. Here we're talking about the set of congruence classes modulo n. Okay? And this is not just a set, okay? It's also a ring. And the thing is, it's isomorphic to the direct product of congruence classes mod A and congruence classes mod B. So, and what does it mean? It means that if you're looking at all the elements that are congruent to an X mod n, it's the same as fixing elements mod 2 and elements mod 3. In particular here, the example would be, can you find the x's mod 5, here we have a equals 2 and b equals 3, can you find the integers mod 5, x mod 5, such that they are congruent to 1 mod 2 and 2 mod 3. So by saying this, that it's congruent to 1 mod 2, I'm fixing the coordinate here. And by saying that it's congruent to 2 mod 3, I'm fixing the coordinate here. And what it means is there is only one congruence class in Z mod 5Z that corresponds to this. So here, because the numbers are so small, there's an immediate solution that x equals 5 satisfies that it's a number between 0 and 5 that will satisfy x is congruent to 1 mod 2, and you can verify that immediately, and x is congruent to 2 mod 3. And that fixes all the numbers congruent to, so all those x's solutions are going to be x congruent to 5 modulo 6. Okay, so here we have that we have fixed all the solutions by finding one element congruent to 1 and mod 2 and 2 mod 3, and there are generic techniques to allow for this. Here we just eyeballed it, okay? And of course, this generalizes very easily to the case of k coprime elements, and so in this case you'd have more equalities, okay? So another important notion here that we'll need, and that's at the heart of Shor's algorithm, is the notion of units modulo n. We say that a class is a unit if it has an inverse for the multiplicative operation. So what it means for A is that there should be B such that A times B is congruent to 1 mod n. So we know that the congruence classes are in one-to-one correspondence with the 0 to n, the A between 0 and n minus 1, such that A is coprime with n. Okay, so we know exactly among those elements between 0 and n minus 1, we know exactly how to identify which ones have a congruence class that's invertible modulo n just by testing if the GCD of A and n equals 1. Okay, if that's the case, we're dealing with an element who is a representative of a class that is invertible mod n. Now, we denote the group of classes that are invertible mod n by Z mod n Z star. Okay, so star is for the group of units. And the cardinality is the Euler function. So the Euler function, it has, so in the simplest case, phi of a prime, p is p minus 1. And phi of a prime p to the t is p to the t minus 1 times p minus 1. You see, of course, that the second expression generalizes the first one for t equals 1. And then if k, so if a and b are coprime, that's a very important one here. We have that phi of ab equals phi of a times phi of b. Okay, and that gives rise to the general formula that if n is p1 to the x1 times p2 to the x2 dot 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 until pk to the xk, if that's the prime factorization of n where all the pi's are different primes, then we have that this is phi, so phi of n is equal to p1 to the x1 minus 1 p1 minus 1 times p2 to the x2 minus 1 times p2 minus 1 dot 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 until pk to the xk minus 1 pk minus 1. So that gives us a strategy for finding the Euler phi function of any general n. So let's work it out in a few examples. This is going to be 2 because we're dealing with a prime. Here, this is going to be, so this is phi of 2 to the 2. So that's going to be 2 to the 2 minus 1 times 2 minus 1, okay, which is also 2. And then phi of 12 equals phi of 3 times phi of 4. We both just calculated them. So that's 2 by 2 equals 4. Now, one of the most important feature of Shor's algorithm is that it's an order finding algorithm. So in Shor's algorithm, we're just we have n, which is given as an input, and we're going to draw an a at random, and we're going to try to find the order of a. And here we're going to say, well, what can we do once we know the order of a mod n? Okay, and it does not always work, but we'll show that with constant probability we can factor n, and by that I mean finding a non-trivial factor of n. So here is the hope of Shor's algorithm, finding the order of the class, okay? And what it means is it's the smallest r such that a to the r is the class of 1, okay? Now, if r is even, which is of course something that we'll figure out, whose likelihood we're going to have to figure out, then the fact that n divides a to the r mod 1, okay, which is directly coming from here, means that we're going to have this identity. And then what we hope, again, something that whose probability we'll need to assess, if those identities hold true, then the GCD of n and a to the r over 2 minus 1, or plus 1 if you prefer, will always generate a non-trivial factor of n. Okay? So let's see this on an example. So here we have a equals 4, r equals 2. So the GCD of 15 and 4 to the r over 2, which is 1 minus 1, is the GCD of 15 and 3, which is 3, and 3 is a non-trivial factor of 15. Hence, if this was the problem, factoring 15, then we would have succeeded here by knowing the order of 4 modulo 15, okay? So this is a trivial illustration, of course. But let's go back to now the probability of having parameters such that the order of a modulo n really gives us a non-trivial factor here. So we're not sure, it is not for sure. So the two things that we need to ensure is that r is even, okay, because otherwise r over 2 is not going to make sense. And the second thing that we'll ensure, and we'll find out the probability of it, is that n does not divide a to the r over 2 minus 1 or plus 1, okay? So first point, if p is an odd prime, the order modulo p of a is even with probability 1/2. So remember, so here we're not dealing with the order modulo n, but first we make a detour by showing that the order of order of a modulo p, the prime, is going to be even with probably 1/2. So we imagine here, we assume, and that's very important here to specify that, we assume that a is generated at random, uniformly at random, in z, so units mod p, okay? So we assume that we're drawing a at random in this, okay? The units mod p. So we know that this that a is going to be invertible. Now this group, we know it to be cyclic, okay? So that's a well-known result that Z mod PZ star is a group of the form G, okay? So everything is a power of G in this group. In particular, we know that A in this group is going to be G to the power some K, okay? And that K is going to be between 0 and P minus 1, okay? Now, we have, because drawing A at random is the same as drawing K at random, what we have is that K is going to be even with probability 1/2, and K is going to be odd with probability 1/2, okay? So K odd with probability 1/2. Okay, now what do we know? What do we know about the order R of A? We know that A to the R is equal to 1, but also it's equal to G, G to the K times R, okay? And so because because P minus 1 is, because P minus 1 is the order of G, then what we have is that P minus 1 must divide K times R, okay? But P minus 1 is even, and then with probably 1/2, and that P minus 1 is always even, but with probably 1/2, K is going to be odd, and therefore, so I'll say with probably 1/2, and therefore, whenever K is odd, which happens with probably 1/2, R must be even. Okay? So what we have here is that in the case that happens with probably 1/2, that the K that defines A is odd, then R, the order of A, must be even. Okay, so we have our first point here proven. Now we assume, now we're looking for the properties of the order of A modulo n. Now the class of A in Z mod NZ star, we've seen through the Chinese remainder theorem, is in one-to-one correspondence with a pair of classes, let's call them A sub 1, which is in Z mod PZ star, and then A sub 2, which is in Z mod QZ star, okay? Now, because of that, the drawing of A in Z mod NZ star, so now we assume A is drawn at random in this group, is the same as drawing A1 at random in Z mod PZ star and drawing A sub 2 at random in Z mod PZ star. Okay, and so each of them have an order R1, which is even with probability 1/2, and the second one has an order R2, which is even with probability 1/2. Okay, now what we have is that A sub 1 to the R is equal to 1, and A sub 2 to the R is equal to 1 as well, and that's because we have this morphism between, which maps a class mod n to the class mod p and the class mod q. Okay, so if you have that A to the R is congruent to 1 mod n, then necessarily P is going to divide A to the R minus 1, and so A is going to be congruent to 1, a to the r is going to be congruent to 1 mod p and mod q as well. And so what it means is that r1 must divide r and r2 must divide r as well, okay? And so the probability of r being even here is at least 3/4, because what we know is that the only possibility for us not to be able to derive from this that r is even is if r1 is odd and r2 is odd, which is something that happens with probably 1/4, okay? Otherwise, we have, in any other possibility, we have r is divisible by an even number, which is either r1 or r2. So now we know that the order of a mod n is even of probably 3/4, which was our first condition. Now we're moving on to the second condition. We're trying to find out that when r is even, so we're assuming that now, and we want to know when r is even, what happens? Do we find a non-trivial factor or not? So now we want to show that n does not divide a to the r/2 minus 1. So here, let's define b to be a to the r/2, okay? And which is possible because we just assumed that r was even. Now, what do we learn from the fact that a to the r is congruent to 1 mod n? Well, it means that we must have that b squared is congruent to 1 mod n, and so it's congruent to 1 mod p, and b squared is congruent to 1 mod q, okay? Now, individually, because p and q are odd primes, individually this means that we have that b is congruent to plus or minus 1 mod p, and b is congruent to plus or minus 1 mod q, okay? This is a property of that only is satisfied if p and q are odd primes here. So, by the Chinese remainder theorem, we're able to identify the b, so the congruence class of b modulo n, right, by the choice of plus or minus 1s here. So there's 4 different choices of arrangement. So there's plus 1 plus 1, minus 1 minus 1, plus 1 minus 1, minus 1 plus 1. And we get 4 choices. 2 of them are, so we have the plus 1 and plus 1, which will yield b congruent to 1 mod n. And if we have minus 1 minus 1, then this will yield b congruent to minus 1 mod n, okay? And these are the 2 conditions where n will be dividing b plus or minus 1 mod n, okay? Which is what we do not want. But in the other cases, which is plus 1 minus 1 or minus 1 plus 1, then the b that we get, the class of b, is going to be different than the class of 1 and the class of minus 1. And in turn, this means that this condition here is satisfied, okay? And this will happen with probably 1/2 because we had 4 choices, and 2 of them were the ones where n divides a or b minus 1 to b plus 1, and 2 of them are the cases where this doesn't happen. So this happens with probably 2/4, which is 1/2. And finally, what is the probability that both conditions happen? Order of a mod n and n is even and n does not divide this. Well, it's simply, of course, the multiplication of those 2 elements. So first, you have the probability that r is even, and then the probability that given that r is even, we have n does not divide a to the r/2 plus or minus 1. Now, one last thing is continued fraction expansions. At the end of Shor's algorithm, we need to perform a continued fraction expansion. So continued fraction expansion is approximating a number with a fraction of this form. Now, the calculation of continued fraction expansion of a number is done by doing this recursive method. You start with you calculate coefficient a0 to be the floor of x, and then say, well, the approximation of x is a0 plus an epsilon 0, which is the fractional part. Now you invert the fractional part, and then again, it gives you an integer part a1 and a new fractional part epsilon 1 between 0 and 1. And then you continue that process by inverting the fractional part epsilon 1. So every time here, you see here you start with x is approximately a0. Here you know that now x is approximately a0 plus 1 over a1. And here what you learn is x is approximately a0 plus 1 over a1 plus 1 over a2, where a2 is the integer part corresponding to the inverse of epsilon 1. Okay, so you can continue this process. Let's do it on an example. So you can do, we're going to be interested in the case of fractional, of expansions of rational functions, but let's see what happens with an irrational number. So pi, the floor is 3, okay? And so what you have is a0 equals 3, okay? And epsilon 0 is approximately 0.14, 15, 92, 65, whoops, 65, etc. Now, we have 1 over epsilon 0, which is 7, plus 0.062513 dot dot dot. So this is our epsilon 1, this is a1. Now 1 over epsilon 1 is going to be 15 plus 0.99654 dot dot dot. This is going to be epsilon 2, and this is going to be a2. And so what we can tell is that pi, at least it gives us the first terms of the continued fraction of pi. It's 3 plus 1 over 7 plus 1 over 15 plus 1 over 1, and of course you could continue, but here we stopped, okay? So this gives us a fraction. If you stop here, of course, you can calculate this is 3 to the 355 divided by 113. The more you continue, the more the numerator and denominator will grow, okay? Now, the very important part that will make Shor's algorithm give an answer is that we know that if x is a rational number and p over q is another rational number that satisfies this inequality, so it's close enough in some sense to x with respect to a denominator q, if that inequality is satisfied, then p over q is a convergence of the continued fraction expansion of x, which means that it will appear in the sequence of fractions that approximate x in the continued fraction expansion of x. So this concludes the prerequisite elementary number theory that we need to know for Shor's algorithm. I thank you for your attention, and next week we'll be studying Shor's algorithm itself, which is how do we get the order of A modulo n. Today what we showed was what to do with that information once we have it. Thank you very much.